Right. Another impact of volcanic ash is directly on jet air traffic or jet airplanes, any aircraft really. Ash is extremely abrasive and it actually melts at engine operating temperatures at cruise altitude, and so you can actually cause engine failure when a jet runs into an ash cloud. So Alaska here is located in proximity to the no-pack flight routes. These carry commercial air traffic from the northern North America to Asia primarily. There are also polar routes that come across the northern part of Alaska. These dashed lines in this diagram from the Alaska Volcano Observatory show some of these no-pack flight routes. The airplanes are just symbolic of airplanes traveling on those routes. And the clouds that are shown here, the different colored clouds from the different volcanoes, those are shown coming from these volcanoes and drifting with the upper level winds through and over and into these flight paths. There have been a number of ash aircraft encounters worldwide. This graph actually shows a subset between 1973 and 2000. And so the blue squares are airports that were affected by ash. So that means ash clouds or ash fall drifted into airspace around those airports, causing the airports to have to close down. The red dots are significant jet ash encounters. So that would be an encounter that causes severe engine damage or damage to the aircraft. You can see that there have been a number of these events, typically circling the Pacific Ocean basin, where we have a plethora of active volcanism because of subduction along the margins of the Pacific Plate. But there have been other encounters as well in Iceland and in Northern Africa and in Eastern Africa. So here's a cutaway cross-section of a jet engine, just a schematic diagram. The inlet air intakes come in through here and they circulate through the engine. There's a hot section back here where the fuel is heated and expelled out, pushing the turbine blades that propel the airplane forward. You can see that ash coming in with the inlet air will circulate through the engine. In the cold sections, the hard ash particles will cause abrasion and damage the delicately engineered metal parts inside of the engine. After the hot section, the ash actually can melt up enough so that it melts. It heats up enough so that it can actually melt. It'll coat turbine blades, it'll clog air orifices, it'll clog burners, it'll basically shuts the engine down immediately because it freezes all over the inside of the turbine section of the aircraft engine. So here's some photos from NASA. A NASA publication showing some engine damage from different ash aviation incidents. So the top one here is British Airways damage after the 1982 Wollongong encounter. You can see this is a turbine blade from inside of a jet engine, and it's coated with this gloopy looking stuff. This is ash that came in and melted in the hot section of the engine and then was spewed around by the turbine blades before they stopped spinning. When the engine stopped, because the ash basically shut the engine off, the ash cools down and forms a coating of glass all over these turbine blades. You can see here pitting and scouring in the upper right corner and clogged orifices. You can also see pitting and scouring on the leading edge of these titanium alloy turbine blades in the lower right. And then in the lower left, you can see little cloddy things on these string materials. Well, this is a cabin air filter, and you can see the tiny little particles here are ash grains. They're actually smaller than the mesh that's formed by the fiber air filter. So ash can actually get into the cockpit and the cabin area of an aircraft through the air filter. So this table chart and graph shows the melting point of different components of volcanic ash. So we have different minerals: plagioclase, quartz, pyroxene, magnetite, volcanic glass, and hornblende, and their hardnesses are given here. They're all 5s to 7s, so they're pretty hard minerals. The melting points are given here in ranges for silica content variations. So you'll see that most of the melting points of these materials are between 1118 for plagioclase to 1550 C. Quartz is really hot, 1713 is its melting point. Pyroxene has this range, magnetite is about 1000 C, and so on. I plotted those ranges here on this plot. So the y-axis here is percent composition of SiO2, and the x-axis is temperature. I didn't label it, sorry, but I could tell you, so you'll just have to keep that in mind. Magnetite here is an oxide. It melts at 1000 C. Hornblende is pretty cold. It melts at about 840 C. Plagioclase has a range. So does glass. So does pyroxene and quartz. This blue line here is the temperature of the hot section of a jet aircraft engine at cruise altitude. Anything that melts at a lower temperature or an equivalent temperature to this will melt. So you'll see all of the volcanic glass, most of the plagioclase, the hornblende, and the magnetite. Some of the pyroxene will melt inside that engine. Quartz has a high melting point, so it doesn't melt inside the engine, but it's also quite hard, so it'll do a lot of abrasion damage. So pyroclastic density currents. We talked about this in great detail in a prior lecture, so now we're just going to focus on a review with some of the hazards that these pose. So they flow mostly down valleys, so that means that areas at risk are largely in valleys. So watch the LinkedIn YouTube videos of pyroclastic flows in your course materials folder for this module lecture in Blackboard. Pyroclastic flows are hot. They'll come out at magmatic temperatures, so in excess of 700 C. They cool as they flow, but they still retain a lot of heat. So it's not unusual for a pyroclastic flow to be 200 to 700 degrees Celsius as it's flowing on the outside of the volcano. They'll burn, bury, abrade, crush everything in their path. They move really fast. Formed by collapse of a lava dome or collapsing ash cloud. Here's a picture down here again from Unzen volcano in Japan showing the destruction and devastation that could be caused by a pyroclastic flow. So here's an interesting hazard map. And excuse me, it shows pyroclastic density current hazards from Unzen volcano. On the right, you can see a photo. This is Unzen volcano up here. You can see it's still steaming. You'll see this light gray to white background pathway that's streaming down the flanks of the volcano running through this farmland area. That is the pathway the pyroclastic flows were taking. When they were hot, they flowed down this valley. You'll see some reddish singed areas outside of that flow pathway here and over in here. And those are areas of vegetation that actually were burned by the passage of that hot pyroclastic flow. This map over here shows a geologic map showing the hazards of different phases of this pyroclastic flows from Unzen volcano. So you can take a look at that and study it to see just where all of the different hazards associated with those pyroclastic flows were going. The blast phase can knock down trees. Surges are more mobile. They can run up over ridges. Hot gas can burn regions outside of where the flow actually is moving. So here's a Google Earth map showing Italy and Vesuvius volcano in particular here, which is down towards the southern part of Italy, just right outside of the giant city of Naples. Vesuvius is in a populated area. Near Naples, there's greater than 1 million people that live around the flanks of the volcano. This is a photo that I took in 2007 while doing some fieldwork at Vesuvius. You can see Vesuvius here in the background. You can see all of the city here in the foreground stretching out around the flanks of the volcano, all the way over around into here. You'll see the Adriatic Sea here, the ocean. You'll see that there's a lot of city hemmed in between the ocean and the volcano. This is actually not a very great situation. It's a pretty high risk situation. So there are over 600,000 people in the red zone that are in danger of pyroclastic flows from Vesuvius. This is a colorized satellite image showing Vesuvius volcano and all of the combined city of Naples and all of a bunch of the other cities around the flanks of the volcano. You'll see that Naples over here on the left-hand side of the image is a very densely populated city. There's a lot of people that live in Naples. You'll see the Naples harbor here. You'll see the coastline. You're going to see a bunch of city that's stretching out along and underneath and between Vesuvius and the ocean. The red zone is outlined extent of pyroclastic flows from the 1631 eruption of Vesuvius. The 79 AD eruption of Vesuvius was actually bigger, so this is a minimum hazard zone. This is inside this red zone. People who are located inside that red zone are at high risk for pyroclastic flows. It's over 600,000 people. Ash fallout is going to be heavy down in the lower right corner of this map. And so the ash fall hazard with roof collapse extends outward from the pyroclastic flow hazard field. It's a very dangerous situation. All right, I have some LinkedIn YouTube videos that talk about pyroclastic flow hazards and other hazards. So again, you can stop this lecture at any time and watch those videos and come back to this lecture when you're ready, or you can, however you want to watch those videos, but I do encourage you to watch them. So let's get into the topic of risk and probability analysis, because these are concepts you're going to need to complete your homework. Volcanic risk is actually quantifiable, and here's an equation. Volcanic risk is equal to the hazard times the value of property times vulnerability. The Auckland, New Zealand scenario cartoon, I'm bringing that up again here because I think it's really easy to see that you have a hazard and you have property value around that hazard, and you have vulnerability around that hazard. So that cartoon actually embodies that equation quite well. So for Vesuvius on the right, you can see another map from a different publication showing the different hazard zones around Vesuvius. So you have the hazard from Vesuvius, you have the value of all of the city and property and people living around the volcano, and then you have vulnerability, how resilient, how mitigated the hazard is, how well prepared they are, or how poorly prepared they are. So we can revise that equation and say volcanic risk is now equal to hazard times value times vulnerability minus risk mitigation efforts. So in this case, if you have a very vulnerable population, but you go in and you say, okay, we can do these things to help mitigate that risk, we'll lessen the chance of a pyroclastic flow going in this direction from the volcano because we've done some engineering or whatever those risk mitigation efforts. You might have a much better educated population. You might install accurate warning systems, for example. So that cuts down on the vulnerability, so it reduces volcanic risk. So for your homework's problem set, you're actually going to use eruptive histories to help evaluate future risk. So I'm showing another example here from a publication about Vesuvius volcano. And this graph shows going back in time from present, which is 0, all the way to 20,000 years ago, the volcanic explosivity index of different known eruptions from Vesuvius. And Vesuvius is a very well observed volcano because it's been frequently active. It also has occurred in a part of the world where people were writing down what they saw from from a long time ago. So proximity to people and the ability of people to preserve what they observed has made this a very well-studied volcano. So most recently, you can see from 0 to about 5,000 years ago, Vesuvius has been quite active. We've had, Vesuvius has had a number of VEI3 eruptions. It's had a number of VEI4 eruptions. It's had a couple VEI5 eruptions and even 2 VEI6 eruptions. Stretching back prior to 5,000 years to 20,000 years, you can see the record is a lot more sparse. This is going to be a consequence of possibly a couple of different reasons. One is maybe the volcano was not as active during that time period. The other is we probably just don't have a complete record of all of the eruptions from Vesuvius between 5,000 and 20,000 years ago. So we're making a big assumption here. We're assuming that past activity informs us accurately about the future. So how long and well known the eruption history is gives us a good idea of how complete our knowledge is to make a forecast. We need to know how many events the volcano had. We need to know how big those events were. We need to know where all of the hazards went. So a well-studied, well-documented volcano provides a much more accurate data set for statistical projections of future activity than one with a short or poorly documented record. So you really need to know the geology of your volcano in order to make a really more accurate forecast about what it might do in the future. So for your homework set, you're going to use a quantitative Poisson analysis to estimate what future percent probabilities are of a certain type of eruption from a given volcano, given what you know of the past. So it relies on a couple of assumptions. One is past eruptions happen randomly with time. Look at the example from Vesuvius again and see if you think the whole record is random or not. Good hint, it actually is not evenly distributed. It depends on a statistical likelihood that an eruption will occur during a certain time period in the future. So we have the Poisson equation here, where P is the probability of a future event. It equals 100 times 1 minus e to the minus little t divided by big T. So this percent probability is reliant upon the probability evaluation window in years. So that's like, you want to know what the probability is within the next 25 to 50 to 100 years. That is the probability evaluation window. Big T is the reoccurrence interval of eruption in past years. So you count up the number of eruptions that happened, in this case from Vesuvius. You can count all these eruptions, and you can divide that number by 20,000 years, and you can come up with numbers of eruptions per year. That's your reoccurrence interval. So here's an example from Lockwood and Hazlitt. This is for Hualalai, Hawaii, and this is kind of a concept that I used to develop your homework problem set. In this case, you want to know what the odds that a lava flow is going to impact a proposed development site in this location in Hawaii. Hawaii is a really nice place. People like going there for vacation. They want to build fancy, expensive resorts to attract tourists. So this is a pretty apt example. So on this map, your proposed development is located here. There's a geologic map that shows lava flows and their ages on this map. And this map shows these lava flows entered the area over the past 4,700 years randomly. So flow number 1 is 150 years old. Flow number 2 is 1750 years old. Number 3, 2150. Number 4, 2410, and so on. So you can calculate the probability that a flow in the future is going to impact this proposed development site by first calculating the recurrence interval. So that means you have 6 flows here, and the 6 flows, you have 783-year recurrence time, which is equal to 4,700 years, which is the entire time record of all these lava flows, divided by 6. So that's the number of flows that occurred in the 4,700-year time period. So what this means is that, on average, a lava flow impacts this region of Hawaii every 783 years. So you can estimate the probability of a future event of lava impacting the proposed development site using the Poisson equation. So you have this number line that shows the distribution of lava flows with time. Again, ask yourself if this is actually truly random. It's really hard to determine that sometimes. And table 1 shows the sample calculations, probability in percent of a future time interval where a lava flow is going to impact the proposed development site is given here. So in 10 years, the probability is 1.3%. 50 years, it's 6.2%. 100 years, it's 12%, and so on. So that's calculated by putting this little t into the equation, divided by big T, which is the reoccurrence interval in years. So that's a quantitative, or really semi-quantitative way of estimating the percent probability of a future event based on its past record of activity from a volcano. There's another method, and this is a way that volcanologists can convey best guesses about what a volcano is most likely to do based on current monitoring data and an understanding of past eruptive history. So this chart, again, here is from Lockwood and Hazlitt. It presents a non-quantitative assessment of volcanic risk It's called a probabilistic event tree. And we're evolving these days towards more sophisticated, more quantitative models using Bayesian statistics and fancy Python code. But for this class, I think it's really important that you know just the basics of how an event tree works, because they are used by volcano observatories to help estimate and forecast what might happen next at a restless volcano. So these are constructed based upon a series of questions. First, you have an observation that your volcano is restless. That means it may be showing some elevated seismicity, it might have some new gas coming out of the vent, it might be deforming, and so on. So the first question you need to ask is, based upon the geophysical monitoring signals you're seeing, do you think the volcano is going to erupt soon? So you need to put in some observations and some past data that you've collected for this given volcano to say, okay, in the past, it erupted more often than not with these types of signals. So we're going to say there's a 65% chance that yes, it will erupt. So the converse of that is the other 35% probability would be no. And if that happens, the unrest ends and the volcano doesn't erupt. But if it does progress to the eruptive phase, you want to know, okay, what kind of eruption might occur? This is where geology comes in, because the geologists have mapped out what's happened at the volcano in the past, and they know that in this particular case, this volcano typically erupts explosively. Sometimes it produces effusive lava flows, but the majority of the activity is explosive. So that means that there's an 80% likelihood that this eruption would be explosive, 20% likelihood that it's effusive. So you can see that this tree starts branching and getting more and more sophisticated and complicated depending upon whether you have an explosive or an effusive eruption. The explosive eruption pathway says, all right, there's an 80% chance of tephra fall, 20% chance of pyroclastic flows, and then you can go on here after you've mapped out the likely hazards to the areas around the volcano that might be threatened, and so on. So I'm going to show you an example of use of an event tree from Four-Peaked Volcano, which had a giant steam explosion in the fall of 2006. Four-Peaked is a volcano located here in southern Cook Inlet. It's actually visible from Homer on a good day. It's about 150 kilometers to the southwest. There's scant evidence for eruptions within the past 10,000 years. The photo down here on the lower left from AVO shows a glacier-covered mountain, basically. Really, really hard to do geology on something like this, so there's a very poor record of past eruptive history. So volcanologists considered Four-Peaked a quote-unquote old, dead, glaciated, hydrothermally altered volcano. Old and dead. Well, Four-Peak actually erupted. September 17th, 2006. Here's a picture of two giant eruption plumes coming from Four-Peak. Came totally out of the blue. It wasn't a monitored volcano. The explosion started at 12 o'clock, ended at 9:45. So phreatic explosions continued during this time. They reached 20,000 feet. We were able to get a sample. The ejecta, or the tephra in that sample, didn't have anything in it that indicated magma was present. It was all hydrothermally altered rock and minerals. Melting of glaciers created lahars containing large blocks of sulfur-rich rock. So these explosions were visible from Homer, and it really alarmed people. So the Volcano Observatory got together and tried to construct an event tree. So, I'm sorry, another couple photos here. The explosions breached the glacier, creating melting, debris flows, sulfur-rich material ejected onto the snow. So there was evidence of heat and magmatic activity, but no magma came out, just these steam explosions. And here's a photo I took of this ejecta. It was really no glass. They were all just crystals, fragments of hydrothermally altered minerals, quartz, older rocks. No evidence for any juvenile glassy magma. It looked just like a steam explosion. Lahars and debris flows continued during and after the explosions. So there was no monitoring network. The earthquake activity continued through late October, so AVO installed a bare-bones seismic network, and based on this unrest that continued after these initial explosions, AVO had to decide how to handle a potential crisis from a dormant or even extinct volcano with no eruptive history data. So we constructed an event tree. So this is quite an interesting exercise for a volcano that we knew very little about. We started with a restless volcano. We said, okay, we had some steam explosions. Those often precede a magmatic eruption. So we thought, all right, it's really 95% likely there's magma involved. So does that magma proceed to a magmatic eruption with ash? And so on. 70% likelihood of a magmatic eruption, 90% likely that it would produce ash. We'd have ash to greater than 20,000 feet, and would we have ashfall? Uncertain. Okay, so there is high probability that new magma invaded the volcano, and the unrest is related to an impending magmatic eruption. So we took this pathway, and AVO started to get prepared for a prolonged eruptive period of eruptive activity from four-peaked. So magma, magmatic eruption, ash producing, ash to greater than 20,000 feet. That's what we thought was going to happen. Instead, what happened is the restless volcano probably had magma involved, but it created a phreatic steam explosion, some melting of the glacier, some local lahars. We never had a magmatic eruption, so it was probably a shallow, failed magmatic intrusion. So the real scenario unfolded differently than we expected. And the reason is because we really didn't know much about four-peaked. We never had any resources to study it. We had no eruption history from geology. We just didn't know anything about it.